Good morning, everyone. Thank you for joining us this morning for our webinar with WMC Water Management. My name is Jason Crawford. For those of you who don't know me, I'm the Director of Membership and Industry Relations at Food and Beverage Ontario. We like to partner with our member companies such as WMC on subjects and topics that are relevant to our sector and things that we're going to help our sector. Our job as an association is to support the sector and again, providing tools and resources. So these partnerships with companies like WMC are incredibly valued, and we appreciate their help in putting this together. So with that, I'd like to introduce John Damiani from WMC Water Management. John's going to take over from here. Once John's done his presentation, then we're going to open up for Q&A. So once John's done, we'll open that up. So with that, I'll pass it over to you, John.
Thanks, Jason. Appreciate the intro. We're definitely glad to be, we're new members of FBO, so we're definitely glad to be a part of this. And the whole idea here is just to bring forth some information that you might be able to use at your facilities or your sister plants or anywhere throughout where you're maintaining any of these types of facilities. So today we're going to be talking about evaluating and elevating cooling water treatment. So really we're focusing on evaporative cooling systems, and those can be cooling towers, evaporative condensers, and refrigeration systems, even fluid coolers in some cases. But these all have very similar ways of operation and similar considerations in terms of water treatment. So as far as, just so you know who you're talking to, by way of introduction, so WMC, we're a water management company. We're fast growing, we're Canadian based. And we're also an engineering firm, so we're really focused on design and service as opposed to just the chemistry side of things. What we do is we use proven technology. We have a high level of expertise, and we really try to deliver the best service to help our customers use less water. We really focus on this idea of using less water because a lot of other things come along with using less water. If you use less water, that means you're using less energy to transport that water and to move it throughout your system. And to heat and cool that water, for example. You're also using less chemistry to treat less water. So if we really focus on water, which is our expertise, there's a lot of other savings that come along with that. Just a quick bio, WMC is established in 1993, so we're 32 years in business now. We've currently got 4 locations serving across Southern Ontario and Quebec, entire province of Quebec. We're trying to grow across Canada, but that's where we're at right now, and we're really happy to continue expanding and trying to work with more Ontario firms. We are a licensed engineering firm, as I mentioned, so we hold a C of A, which means that we're allowed to offer services directly to the public, and we can advise our customers directly without having to engage third-party engineering. And another thing that we're really proud of is we're 100% Canadian owned and operated. And as far as why we exist, so for any facility that uses water, good treatment of that water is going to mean lower operating costs. It's going to mean longer equipment life, less downtime, better sustainability. This is really a big important piece to think about in food and beverage, where your margins are very thin. Plants can have as little as 24 or 48 hours per year for planned shutdowns, right? Outside of that, you're operating 24/5, 24/7, and there's really no margin for error on that system. So these types of considerations are really important. So our role is to really help our clients achieve better results on these objectives through really considering and improving their water treatment. Okay, so again, we're talking about cooling water treatment, and for any water treatment, there's a complete water management program that we want to make sure the customer understands and wants to implement on their system. That doesn't just include chemistry, right? The chemicals are only one component of this. There's engineering that goes into it, being the design of the program. There's service, obviously having all the right pieces in place, but not executing on that in terms of monitoring the system. Having the right controls in place and the right equipment to begin with. All these things come together, and they need to be working properly as a unit in order to deliver correct water treatment on the system. Okay, as far as the objectives, we want to preserve our operating costs. We want to prolong the equipment life. We want to prevent unplanned downtime, and we want to protect the environment and the public. Okay, so those are the 4 really high level objectives that we have on any water treatment system. And if we were to kind of tie some dollar amounts to that, where this really all comes down to costs and what we can really avoid and prevent in terms of absorbing too many of these costs. Operating costs are obviously your day-to-day, your utility expenses, your water bill, your energy bill, your chemical spend. That's definitely your top line, and that's the biggest impact and the fastest impact that you have from the results of your water treatment. The equipment life can be a higher cost than that, and now we're moving from operating to capital costs, right? So if we have an unexpected or premature failure on a piece of equipment, well, now we've got a big capital cost on our hands, right? Downtime is a really big one, especially in food and bev. I've had customers tell me, when we're considering, for example, a redundancy measure to improve their equipment, so that it's not necessarily going to give them a direct improvement, but it will prevent them from having unplanned downtime because we've got backup. That investment, I've had customers tell me how many minutes of production that if this solution saves them, or this recommendation would save them, would make it worth it. So there's a lot of money moving, and there's really thin margins, so we really need to consider downtime as a really high cost. And then protecting the environment and the public in a lot of ways can actually be the highest cost, right? So none of this is worth it if we're getting people sick from waterborne pathogens, or if there's engineering problems or equipment problems that are causing failures that are creating safety risks, right? All of those things. We're not talking necessarily even dollar signs here, right? But the cost can be the highest of all in those cases. Okay, so as far as things we're trying to avoid in the system and the considerations that we have, one here we have is corrosion. So corrosion can come in different forms on a cooling system. We have general corrosion. We have MIC, which is microbiologically induced corrosion. Another quick way to say that would just be biocorrosion. And we have white rust, which I'll talk about a little bit more detail later. But general corrosion is basically just the whole idea that water plus metal always will result in corrosion. With any water treatment program, we're really just working to minimize that and not completely eliminate that. It's impossible to completely eliminate all forms of corrosion. But really what we're trying to do is implement a program that extends the life of that equipment as much as possible to where it's within the expected lifespan or exceeds the expected lifespan, and we're not having a premature failure because of an excessive corrosion issue. So we're really just slowing it down as much as possible, using the technology, equipment, and chemistry to slow that down. The biocorrosion is, the corrosion result is similar to general corrosion, but this is really specific to corrosion that occurs as a result of sludge and biofilms forming because a lot of bacteria and biological microorganisms produce waste that could be acidic, for example, and underneath the biofilm, what you can have is corrosion, active corrosion underneath that. And the problem with that type of corrosion is now your corrosion inhibitors, if you are adding those at the correct rate, they're not getting to that part of the metal because it's protected and covered by a biofilm. So the bacteria is actually protecting it and causing pretty rapid corrosion underneath that. And then white rust is specific to galvanized steel, and it's something that we always talk about when we talk about cooling towers, because a lot of galvanized metallurgy exists in the cooling tower industry, from entire galvanized towers to towers that might have a stainless basin, but they still have a galvanized shell. So any galvanized metal present, we need to take measures to protect the zinc coating on the galvanized, because it's very susceptible to corrosion under the wrong conditions. Okay, another consideration is deposits. So we have scale and sludge. Basically, a deposit is just a general term for anything that is depositing onto a surface, usually a higher skin temperature surface, so like where the heat transfer occurs, for example. So these are deposits that we don't want on the system, because a deposit is an insulating barrier to heat transfer. So if we're trying to transfer heat from a cooling system, we're trying to reject heat into the atmosphere inside the fill, or reject heat to the other side in terms of an evaporator or chiller condenser. We don't want deposits on these surfaces. Heat exchangers, the same thing. So this can occur due to overcycling. We'll talk about cycles of concentration a little bit later, just to make sure everybody understands all the terminology. It can occur due to inadequate bleed control, which is part of overcycling. But the bleed from your system, the automatic draining of water to the system, also helps clear sludge out of the system. So it removes some of the suspended solids as well, which can cause fouling. And then you also have low flow areas in the system, which can cause settling. So even an otherwise well-controlled system from a bulk water standpoint might have problems because there's low flow areas where things are settling out into. You also have suspended solids. Suspended solids can come into the system from the outside air because cooling towers are really good air scrubbers. So you can have pollen, leaves, insects, all kinds of things, construction debris coming from the environment, road exhaust, getting scrubbed into the tower and then draining it into the bulk water, and then causing deposits in that way or clogging up strainers. All these things add up to reduced efficiency. So we're impeding the heat transfer because we don't have a clean surface anymore, and that's going to reduce our efficiency up front. And then over time, if not addressed, if we're plugging tubes or if we're really gumming up the system with fouling, that can lead to eventual premature failure. Okay, biofilm. We want to protect against biofilm. So a cooling tower, if you think about it, is a perfect environment for microbial activity. Okay, very rapid growth of bacteria and forming a biofilm is possible. If you think about, if you're trying to design and perfect a perfect environment for growing bacteria, it would probably be something like a cooling tower, big metal warm thing that's got a bunch of water in it that's just got the sun beating on it. It's really a good environment for creating bacteria. So biofilm is specific types of bacteria will actually form a film on the surface. And one thing a lot of people don't know is that biofilm, a lot of people are worried about scale, and they should be, calcium carbonate scale, for example. But biofilm is actually 4 times more insulating than calcium carbonate scale. So and I've got this on a stacked bar because often you see them in combination. When there's big problems in the system, you often see scale and biofilm kind of simultaneously in the system. But if you separated them out, you'd see that, for example, a 1/32 of an inch deposit thickness for scale will get you about close to 10% loss in your heat transfer efficiency. Well, 4 times that, almost another 40% basically would be on top of that for the biofilm. So it really causes a major problem. And then aside from that, I mean, this is a public health hazard in all cases. When we talk about bacteria, we get into things like Legionella monophila is a very serious bacteria that can get people very sick. There's a lot of attention placed on that. The purpose of this webinar today is not to get in depth on Legionella, but we will mention it a little bit. But these are things that we're trying to avoid when we're talking about the microbiological control. So it's not just the technical and the operational and mechanical impacts of the biofilm forming. There's also a safety aspect to it. So that's really important to consider. Okay, so we'll go through the basics of cooling water treatment. Okay, so this all centers around the idea that water that exists in the natural world is not pure H2O. If you look at the chemistry of it, right? All water contains some impurities. Those impurities can include dissolved solids, suspended solids, and dissolved gases. Okay, so when we talk about dissolved solids, we're usually talking about metals, calcium, magnesium, iron. We also have bicarbonates and chlorides, things like that. This is more. These exist at a higher concentration in groundwater, like you'd pull from a well, but they exist in all water. Suspended solids, kind of the opposite. They're more prevalent in surface water, like lake water, things like that. And municipal treatment plants treat for a lot of these things. We're talking about soil and organics and some precipitated minerals that are floating in the system, clay and silt, all these types of things. And that's where all the microorganisms exist as well. And then we have dissolved gases. Water is a universal solvent, so it dissolves gases as well. So there's dissolved oxygen and carbon dioxide that's present in water, and these can cause their own problems in certain types of systems. Okay, so I mentioned cycles of concentration before. We like to just do an overview of this. A lot of people understand what this is, but a lot of people don't. We get a lot of questions from this. So basically, this is really central to water treatment on any type of system. So what cycles of concentration is just the ratio of the total dissolved solids. So if you think about just something, the simplest sort of compound you can come up with, sodium chloride, like salt, that you would dissolve in water. It's the ratio of how much of those dissolved solids in your starting solution of water versus compared to what's actually in the circulating system, right? So in a cooling tower application, we're talking about your makeup, your freshwater makeup as it exists, and then what it looks like inside the cooling tower as it's circulating, okay? So as we increase cycles, generally we want to operate as high cycles as possible, because using higher cycles, and I'll show what that means, Running at higher cycles will reduce operating costs because you're using less water. There's less chemical to treat that water, less energy to reheat or recool that water, et cetera. So it's really crucial to account for, makeup quality, the operating conditions of the system. All these affect the maximum safe cycles that you can operate at. Okay, so here's just a quick example. So if we had 2 liters of initial volume of water, so just a 2-liter bottle of water that has some amount of a contaminant in it, we won't just, let's say this is the total dissolved solids, but let's say this could be just 260 milligrams of a single contaminant like calcium, something like that. So if we have a 2-liter initial volume, underneath that you can see if we have 260 milligrams of our contaminant into 2 liters, that's 130 milligrams per liter. We're dealing with water, so milligrams per liter is the same as parts per million for the purpose of this. So our cycles of concentration is very simple. We're still at our starting sample, so we're just at 1 cycle. So we're considering that is the water that we're looking at is 130, and our starting sample is the same sample. So 130 divided by 130, that's 1 cycle. So running once through is also this is also known as running once through. So if the water going into the system is just used and then dumped directly to drain, that would be running at 1 cycle or once through. Very expensive. There's no cooling system on the planet that would be sustainable running like that. And in a lot of jurisdictions, it's not legal to run like that because it's so wasteful on water. And we'll see why here. So if we were to evaporate 700 mils from that initial 2-liter sample, we'd have 1,300 mils left. So now our sample, our live sample is 1,300 mils or 1.3 liters. So if we have that same 260 milligrams, because what we're doing is we're evaporating only the pure H2O. So effectively, the evaporate, if we were to condense that and test that, that would be 0 milligrams, right? There would be 0 milligrams of that contaminant in there because it's just evaporated pure water. So all we've done is subtracted the volume, but we have the same amount of contaminant in there. 260 milligrams again, divided by 1.3 liters. Now we're at 200 milligrams per liter of concentration. So our cycles of concentration, we just take our current sample, the 200, divide that by the 130 that we started with, because that's our makeup, that's our fresh makeup. So we see we're about just over 1.5 cycles. Okay, if we do that again, and we evaporate all the way down to a quarter of our initial sample, so 500 mils left, 1.5 liters or 1,500 mils evaporated, we do the same calculation. So 260 milligrams, that's a fixed amount. The contaminant stays behind. We divide that by 0.5 liters. Now we're up to 520 milligrams per liter. So our cycles, if we divide the 520 by our initial sample, now we're running at 4 cycles. That gives you an idea of how that operates. And the way we design water treatment is we need to consider this, and we need to compare all these cycles against the maximums that are established either by the manufacturer of the cooling tower or just industry knowledge, the best practices of what we know that we can run at. Also considering, again, the temperatures that are in that system and the equipment that it's exposed to, whether we've got chillers involved or plate and frame heat exchangers or whatever it might be, that's all going to affect what we can cycle. So we can calculate cycles based on total dissolved solids or on individual parameters like calcium or total hardness or chlorides, for example. All these things need to be looked at in order to design the system. So when we get to the objectives, so kind of circling back to those 4 objectives that we came up with, if we call these the key principles of any water treatment program: preserving operating costs, prolong equipment life, prevent unplanned downtime, and protect the environment and public. If we kind of put those at a high level as key principles, how do we design a program, dig in on each of these to create a program? So number 1, for preserving operating costs, well, we want to maintain our heat transfer efficiency by preventing the scale, fouling, and any sort of biofilm, right? So that'll maintain our heat transfer efficiency. That addresses the operating costs. We also want to achieve maximum cycles. That's going to minimize bleed from the system, which is going to conserve water, conserve energy, and chemicals. Okay, so that's how we address that first objective. The second one, prolonging equipment life. So how do we do that? Well, number 1, if we prevent deposits on the heat exchange surfaces, that can lead to blockages and failures, which would lead to premature failure. So if we can prevent that, we're helping prolong equipment life. Same with corrosion. So if we minimize the corrosion rates of all the metals in the system by maintaining the best water chemistry, that will extend the life of the equipment as well, and the piping. On the downtime side, if we prevent fouling, that's going to reduce of all kinds, whether it's scaling or biofilm, that's going to reduce the duration and frequency of any kind of maintenance or cleaning that's required on that system. If we minimize corrosion, it's going to reduce the frequency of repairs to fix leaks and things like that. And if we control the microbiome activity, that's going to avoid unplanned shutdowns to have to do emergency disinfections or clean out the system or things like that. So downtime is also avoided by getting this right. And then finally, as far as protecting the environment and the public, we want to minimize our utilities consumption, right? That reduces our environmental footprint, obviously. If we follow applicable best practices for water safety, that's going to protect the public. You know, there's a lot of cooling systems have very close proximity to the public in terms of, you know, being over top of a parking lot or a pedestrian walkway or things like that. Or even just the staff that work at the plant itself, they're exposed, or they can be exposed to the vapors coming off the cooling tower, the evaporate, or the tower water itself. These are things to consider when we're considering everybody when we talk about the public. We want to deliver products and materials safely and responsibly, and hold our staff to an exemplary standard of safe work. So, we try to set an example at our customer sites of safety and even highlighting things to our customers, and we expect the same in return from them, right? We're all working together to work safely. So all these things are things that we can include as part of our program to make sure that we're achieving all of those objectives. Okay, so digging in one more level, system specific, the program for evaporative cooling. Well, so there's really only 3 things that we're doing. So all of those objectives are really addressed by just these 3 things. So number 1 is bleed control, also known as blowdown. So if you're more familiar with steam systems, blowdown will be the same term. You can use them interchangeably. So bleed control, so that's a mechanical method of keeping the cycles of concentration under control. Second is corrosion control. So we want to minimize corrosion, so we're not rotting out the system and causing premature failure. And then and microbiological control. So scale and corrosion control actually should be both in there, but the bleed control actually addresses the scale control as well. So so there's chemistry that we add for corrosion and scale, but the bleed control is actually the primary way that we're controlling scale. And then, like I said, the microbiome has to be addressed in a specific way with the chemistry. Okay. We'll just go quickly through some fundamentals of the system design. So this is not meant to be a full engineering course, but just to show you a very basic sketch of what a water treatment system looks like. This is the most simple way that you can show it. Okay, so the main thing we have here is highlighted in blue now. And what this is we would just call this a loop. And all we need to do is get flow through the system, through a couple of sensors to be able to measure what we're looking for in the system and decide what we need to do. Okay, so we need a live sample. We can't just drop a probe in the basin, for example, because then we don't know if the system's on or off, for example. So we need some flow through the system. And for any size system, it really doesn't matter what the size of this cooling tower might be. If this is a cooling tower, this could be 1,000 tons, 200 tons, 10,000 tons. Really, we just need a live sample. So this might only be a 3/4 inch line given any system. And in that line, we're just circulating. So we'll supply it from the pressure side of the recirc pumps, return back to the basin or into the suction side. And we've got a couple of sensors that are installed in there. And all we're doing is, number 1, we're measuring the conductivity of the water, or the TDS. Again, it's just a metric that we're using to measure the dissolved solids that are in that water and deciding what to do. So the first stage we have is the bleed system. So the conductivity level is going to be measured by the controller. It's going to have a set point. And when we exceed that set point, that tells us we're too high on cycles of concentration. And we want to open a valve to bleed this high concentrate water. And what that'll do is drain water from the system. And then eventually the level control system on the cooling tower will operate to top up the water level. But the new water coming in is going to be fresh city water or fresh makeup water, which has that lower concentration of all these minerals. And that's how we keep under control. This is an automatic system that keeps doing that. So it's usually a motorized valve or a solenoid valve that'll open, be controlled through a flow regulator, so we bleed at the right rate. And that's the first stage of the program. The second stage of the program is feed. So we often call these a bleed and feed system. So now, as the new makeup comes in, or according to other parameters, I'm showing an ORP probe there as well, so that would be a live way to control one of the biocides. But a lot of the products are fed, for example, proportionally. So you'd feed every 10 liters or 10 gallons of water, you'd have a meter that's sending a ping back to the controller to indicate that new water's entered the system that needs treatment. And then we'd activate our pumps, for example, to run product into there. And that optimizes the chemistry. Okay, so the chemistry that we add complements the bleed program. So the bleed gets things under control as a baseline, and then we add chemistry on top of that to help protect against things like corrosion, keeping sludge and scale forming precipitates from depositing on surfaces, anything that does form in the system or end up in the system through air scrubbing. We want to keep that mobile so that it actually leaves through this bleed system. So usually your chemical feed is a single product that combines your scale and corrosion inhibitors, and then you have a two-stage biocide program. So you'd have an oxidizing biocide and then a non-oxidizing biocide. And they operate in a little bit different ways, just to help keep things under control over the long term. Okay, this is what the system would look like, sort of more in a diagrammatic fashion as far as what the actual boards that look like. They're usually packaged systems. These are the ones that we make. Again, you can see the central controller with a makeup water meter feeding to it. So that as new water enters the system, that's going to send pulses back to the controller to indicate that treatment's required, so that'll operate the pumps. And the bleed system's there, just like you saw in the previous diagram. So it's the water is traveling through the loop, and that bleed valve opens and closes as needed in order to send water to drain. So metering is really important, obviously. So we have, we're metering the water coming in. You can also install, and you should also install a meter on the bleed. And there's two reasons for that. Number one is you can control your chemical feed on either makeup or bleed. And different situations call for different priorities on that, where one may be advantageous compared to the other. You also have the aspect of certain municipalities offer rebates, for example, for water that you've evaporated to the air. So a lot of people will understand, and when they read their water bill, that you pay twice for water. You pay to receive it, and you also pay to send it back to the municipality to retreat it. So there's some jurisdictions, Toronto being one of the main ones, that offer a rebate for water that you can prove, and not every type of application is applicable, but cooling towers are. If you can prove that you've diverted water back from sending it back to sanitary sewer, you can get a rebate on that. So the only thing you need to do is install meters on both your makeup and your bleed, so you can actually run a calculation on how much you've evaporated. And then the second thing you need is just to engage an engineering firm like WMC or someone who's familiar with this to send in the application for you, and then you can get a rebate back. So we've got customers that are getting $20,000, $30,000, $40,000 in rebates per year just from doing this, right? And it can often exceed even the cost of the water treatment program. So it's definitely something to make sure that you're doing if it's something that that is available in your jurisdiction. Okay, just another example. You can see systems like this where it looks more complicated, but really you can see it's just two of the same system mirrored. In this case, it's a food and bev plant that uses fluid coolers, and they're not balanced together with an equalizer line. They're actually separate condenser loops. So you have to have two different treatment systems. We've got a central controller because there's enough ins and outs to control both of them. But again, just an example of what these systems can look like, but they're all doing the same thing. You've got a loop where you're pulling you've got your sensors installed and you're taking your samples from, and then your chemical feed is in the return of that. Okay, we'll talk about passivation quickly. Basically, any cooling tower system that's got galvanized metallurgy requires passivation. So when you have a new system, this is really important. That does include stainless basins, as I mentioned. If the casing in the hot deck are galvanized, you still need to do that. And this is really, it involves operating the system at a low load under specific conditions. It takes several weeks. It can take anywhere from 4 to 12 weeks, usually on the lower end of that, but it can even take longer than 12 weeks in rare cases. But basically, failure to properly passivate a galvanized tower is going to result in white rust formation. So white rust is a compound of zinc. It's usually a complex zinc carbonate compound. And it appears as like a waxy, powdery kind of formation on on the tower, on the heat exchange surfaces, on the actual metal surface where the galvanized is. And it can also transport and deposit elsewhere. But these are definitely signs of problems. You do not want to see this, because this is a form of corrosion. We're not adding, most water treatment programs won't have any zinc component that any zinc would be added. So if you're collecting samples of unknown substances that you're finding in your cooling towers that are turning out to have a high portion of zinc, it's probably because it's coming off of the galvanized coating in the tower. So this is not something that's reversible. This is corrosion. So you want to really do everything you can to avoid this up front. Again, not really the direct focus of this talk, because you can do a whole presentation just on passivation, but we do have some resources available. So if you reach out to us afterward, we can definitely share these. And basically, there's technical bulletins, documents for preventing white rust formation by properly passivating the cooling tower. And another thing to mention is on cooling towers, even systems that aren't galvanized, there is a pre-operational procedure as well. And you'll often see the term passivation used there as well. Mostly that's just convention. It's just we got to passivate the cooling tower. But passivation is a very general term. So when we talk about zinc or galvanized passivation, that is very specific to protecting the zinc coating and passivating so that it's ready for permanent operation. But passivation in the more general sense can refer to passivation of any type of metal. And really there is pre-operational considerations and procedures for non-galvanized towers as well. So we've got a document for both, and you can definitely review those and see the differences. So we can share that with anyone that requests it. Okay, moving on from the actual basics and background to like evaluating the systems. So there's different types of inspections that can be done. One is what would be called a survey. Just a preliminary visual inspection that's based on what we can see today. Really, there's often minimal background information history. So if we're first engaging with a customer, that's basically what we're providing as a survey. Just to come and take a look and give a very high level sort of verbal opinion and kind of determine how we want to move from there, if we need to escalate to something or if we think the system's in okay shape. A routine inspection would be more for a customer. That's kind of a detailed visual inspection. That's usually while the equipment is offline. And the important thing with routine inspections is that they're just snapshots. They're not telling the whole story. It's a trending tool. So it's really about doing the work and taking and completing the inspection and documenting it, and then comparing it to last year's inspection or comparing it to next year's inspection. That's really the useful part of inspections. And then finally, you have audits, which are more of a third-party, sort of non-biased, detailed assessment of performance. And then you compare those back to OEM project specifications, industry standards. As an engineering firm, we get involved in this. It's definitely something that we can offer. Just to give you an example of what a survey might look like, we've got an example one here. So it's, this is what you should be looking for in terms of feedback. If you call somebody to come in to take a look at your system, again, there's very little information that we would have had up front on this, and this is mostly information. Here's just an example, but basically what we're doing is we've got some photos in here just to establish so the in this case this was a food and bev facility, and just so that they know which of their systems, because they have multiple systems, which of their systems are we talking about here. So we're just, I just pulled one page here, but we can see the tower, we can see what the water treatment system looks like as we walked in and looked at it, and we just took some readings, and really we're just kind of establishing, just to understand what equipment that they have, what products they're using, what type of program they might have implemented. So that's what an initial survey might look like. And it would just be like a one-pager like that. An inspection report, similar template, but we're now getting into the details here. So we have actually, a second page here with some interior photos. In this case, this is actually the same customer on their newer system, where they had engaged with us for a while and they'd been running it for a while. So we're just doing sort of a first routine annual visual inspection. So again, an establishing shot, we'll take a picture of the plate, and then interior photos are really important. This is the whole point of the inspection. It's shut down, strained. In this case, we've got a really clean system. This is probably very early in the stage of operation, because you can see it's still shiny. So we're just getting towards, making sure that the program has been established correctly and it's up and running, and the water treatment is ready for making sure that the system gets passivated. Okay. On the opposite end of the spectrum, again, back to that older system at the same customer. This is what it might look like when you have problems in the system, right? You've got active corrosion, you've got historical issues. So again, this is really just about trying to document all those things. In this case, we had a lot. This system had experience, before we took over the water treatment program. This system had experienced, several failures. They had tried to recoat a lot of the galvanized with new zinc coatings. Those had stripped back off. You can see the basin is corroded. But again, the point of this is just to show that documenting everything we can with photos and details is really important. Just so we can establish this as a trend, so we can set the expectations on how the system runs. Okay. So speaking of documentation, you might have something like this where you have a deficiency report. All these things are really important. They come together to make sure that you have a good understanding of how your water treatment is running and how your equipment, the condition of your equipment. As water treatment experts, we are experts on the water treatment component, but the actual, the remaining life and the repairability of the equipment, that's really where you need to kind of combine that with the OEM knowledge and your service company, cooling tower service company, to really understand that. So we often work together with them. But this is an example of what we would call like a deficiency report. And again, we've got on this system, we've clocked that they've got reduced bleed set points on their cooling towers to try and compensate for other problems that they have. The selection of their inhibitors was incorrect. Poor conductivity control. The biocide program was having problems. They had foaming issues, an undercycled system, things like that. So without getting all the details, this is kind of what you're looking for if you're having an audit done of your system. This is an example of what a report might look like as far as actually collecting samples and testing them, and just sort of establishing just the baseline that we've seen as we first come into the building. Some urgent items in this case. And then this is also what we like to see is when we do an audit, we really like to communicate with the customer and make them aware of exactly what's going on. In this case, we had a cooling tower that was fed partially, or supposed to be fed partially, soft water, and we'll talk about that, but that's a strategy you can use to increase your cycles. But in this case, the bypass valve was shut, and they weren't feeding any soft water to the system, and they didn't adjust their water treatment program. So this was causing problems because now they're overcycling on hardness and causing scale and things like that. So just something as simple as this of, the plant's going to know where this valve is. So we show it to them, pictorially, just as an appendix in the report. This type of thing too. So we have water softener that's been incorrectly programmed, again, feeding the tower. So that's part of what's affecting the results. Hey, this is what we looked at when we came into the system and first saw things, highlighting a bunch of issues, just so we can document and see, because the people who review our reports might not necessarily be the people that are on site. We might be presenting this to somebody else, and we need to communicate that. So these types of things needing to be addressed. Fortunately, this here is actually not a food and bev plant, but it's really just to establish the condition that we found the system in, and to give as close of an opinion as possible based on the information that we have. As you can see, a controller, in this case, that set point on the controller is lower than it should be, so it's undercycled, meaning it's wasting water and energy. Okay, so just remediating really quickly. There's lots of remediation options. It's not always the end of the world if you have problems in your system. There are things that can be done to bring it back to normal. This includes physical cleaning. Obviously, cooling tower maintenance is really important. Getting it cleaned seasonally or annually or whatever your schedule is. Chemical descaling, if you have scale, or also known as acid cleaning, can be done. Chemical cleaning with dispersants and online cleaners can be done. There's repassivation that can be done, epoxy coatings. And then on the bio side, system disinfections, hypochlorinations, and then obviously, the worst case scenario being mechanical repairs or replacement. So there are options for remediating things. It's just ideally, if we get the water treatment correct, we don't have to go to these measures. But just to give you an idea what that looks like, here's a tower that had pretty severe scale and biofilm. Like I said, it often goes hand in hand, because if the treatment's neglected, then you usually have problems with both. But here's a product that we use which is an online cleaner. And this is an 8-hour cleaning that we ran. So, I mean, the cost of this is not low because you've got, probably 2 or 3 guys on site for 8 hours, plus all the product that we have to use, but we can get it clean, as you can see. So, and that's online while the system's running. So as we are able to pull those deposits off, you just get, you get a lot of efficiency back. But you can see, look, there's some of the casing of the cooling tower around there, that's been scaled, and who knows what kind of corrosion damage there is elsewhere in the system. But as far as the fill, we can get the system back up online and running. Okay. Finally, last thing we'll talk about is just elevating. So engineering and program improvements so that we can actually get those savings, improve our reliability, and get our sustainability back. So before we kind of talk about these things, the main point to establish here is getting the treatment right and getting your levels under control and having the right controls in place and a program established and the right engagement on site between your own operators and your water treatment company. That's really the most important thing, getting to that point before we talk about elevating. We often get approached with, projects and sustainability initiatives and things like that, like, hey, we need to save water, or we need to, we're going for net zero, or, we're pursuing, LEED or other types of certifications. But really, there's exponentially more savings to be had by just, if there's problems in the system, correcting those problems and just getting to the industry standard baseline before we talk about going to the next step. So that's when we engage with our customers. That's the first thing we do, is we just make sure we do everything we can to get everything up to a good baseline. That's, as we would run the system. So we try to act like, partners with our customers. If we own this facility, this is what we would do first. Then let's talk about improving that and getting it better. So number one, we have reliability improvements. Obviously, that's another sort of mid-stage to going all the way to the engineering changes. But redundancy considerations. I talked about that previously, where if we can do anything to improve redundancy, we're often getting a lot of payback on that. It's not direct in terms of, hey, this is going to drop my operating costs. And in fact, it is a capital cost just to implement it. But if you think about how much downtime it might save you, that's where the payback is. Keeping spares and rebuild kits on hand, again, that's just to keep you up and running. Spare pumps, spare valves, anything that we can do, even spare water meters. We have customers that will keep spares of everything. Water meters would be important in a rebate application scenario, because you don't want to go a long period of time where you're not able to monitor your evaporation, because that can cause problems with your application next year and put your rebate at risk. Remote monitoring, that's a really good one. So, we're in a world where there's not a lot of staff these days able to take care of everything in terms of maintenance. There's a lot of demands for maintenance in the plant itself. So having some remote monitoring where your water treatment company can help you monitor that system and set up alerts so that we can work together to keep that system under control. Super important. I mentioned operator engagement, regular water testing on site by your own staff and keeping logs and, having a system of communication where that's where, anything out of line is reported to the water treatment company. Really important, because that allows you to respond faster, right? So interruptions are going to occur. It's really about identifying those and getting them corrected quickly. That's what's really going to pay off in terms of the lifespan of the equipment, just making sure you don't run out of spec for a long time, right? That's how you risk forming scale or having bad corrosion events, things like that. Emergency disinfection kits, keeping things like that on hand on site, so that if you have a biological spike or a positive Legionella result or something like that, you can take action right away. Okay, water safety, I kind of just mentioned that. All facilities should really establish and maintain a water safety plan. So that should include the risk management measures for waterborne pathogens. This doesn't only include cooling towers; it has to encompass the whole water profile of the building and all hazard critical control points. But yeah, some references on that. ASHRAE Standard 188, Legionella risk management, that's been around for a long time, and a lot of standards are based upon that, including the Public Works Standard MD 15161. So that's what the Canadian government uses for their facilities, and that's as a Canadian standard, that is something that's often referenced. ANSI 12080 is a much more newly established standard that sets up qualifications to be a member of a water safety team, and a lot of reputable water treatment companies, including ours, we'll certify our reps to that standard so that we can lead the water safety plan. So that's, again, it's not the focus of today's talk, but Legionella risk management obviously is really, really important. And establishing that water safety plan, honestly, this is something that, aside from, you know, getting things right first, this is something that you can jump into right away and establish if you don't have one. Really highly recommended, and really just addresses a lot of those concerns as far as the public safety side of things. Okay, moving on quickly, we'll finish off with the some of these engineering improvements that are kind of the more exciting part of the talk. So if we think about, we have a system that's operating as efficiently and well as it can in terms of, you know, the water that is being supplied and the water treatment program that's been implemented. Well, what can we do from there to elevate that and go past it? Blended soft water feed is one thing you can definitely consider. This is required on some systems. So if you're in some Southern Ontario areas like Kitchener-Waterloo, Guelph, there's some really high hardness water because you've got municipalities that are fed well water. So the hardness specifically, but other dissolved solids come in at a very high level. So you just naturally cannot cycle that water very high at all. So you often have to partially soften the water in order to just operate it. But in areas where it's not strictly required, it can be just an improvement on the engineering side. Because if you cycle up water, what you're going to find is that let's use Great Lakes water as an example, Toronto, you're going to find that as you cycle that up, hardness is the first parameter that you hit as a limit in terms of, I can't go past 450 to 550 ppm, depending on my temperatures and everything like that, before I start risking precipitating that calcium out and creating scale. The chemistry can only get you so far, but if we remove a lot of that hardness, that gets that parameter out of the way so that we can cycle it up higher. Okay, it gives us better control of the system chemistry as well. So this is what like a water softener would look like. Again, just very basic diagram. And often you can see at the top there a bypass valve that would just be normally closed for service on a system. So you'd only ever open that if your softeners were having problems or you're just doing some routine maintenance on them. But if you were to replace that with a blending apparatus where you actually in a controlled manner you blend in some mostly soft water actually, and then you blend in some hard water in. The reason for that being you can't feed 100% soft water, zero hardness to a cooling tower. This has to do with the saturation index that you're achieving on the tower. If you have zero hardness, the water is a little bit too corrosive, actually very, very much so too corrosive, where you'll create a corrosion problem by solving your scale problem. So you do need a little bit of hardness in the system, and a blending apparatus will allow you to bleed the correct amount of hard water back into the system. And basically what that allows you to do is let's call it double your cycles. So if you increase from, let's say, 3 cycles of concentration, or let's say 3 1/4 cycles of concentration, and you go up to 6 1/2 cycles, you've doubled your cycles of concentration. And if you think about that from water saving standpoint, the evaporated water is the same. So when you evaporate water, that's your heat reject. So that's fixed. That's based on your load. But the bleed water, the water you send to drain deliberately to keep the system under control, if you double your cycles, you cut your bleed water in half. So that can add up to a lot of water. Okay. Wastewater recovery is another one. So any water that's discharged from other processes can be recovered. There's a lot of potential sources that are suitable for cooling towers. That's a nice thing with cooling towers compared to steam systems, for example. So process discharge, rainwater can be options. The feasibility of this and the benefits that you get depend on how much water is available as waste and what you need to do. You often can't just send it straight to the tower. There's often some sort of pretreatment step that's required. So there's cost. Then you have to really just look at it from an engineering side and see if it's worth it. So this is an example of an RO system, right? So you might have some facilities might have a small lab or some other process where they're actually producing RO water. Well, ROs reject water. Anywhere from 10 to 50% of the water that goes in ends up back down the drain to produce the quality of water that they need. So that depends on the quality of the RO, its size and the flow rates and the quality of water you need out of it. 50% of all your water going to that RO, even if it's half that, let's say 25%, that can add up to a lot of water. So instead of sending it to drain, in a lot of cases that can be sent directly to the cooling tower. So you can have a pretty big saving on that. Finally, another form of wastewater recovery would actually be bleed water recovery. So if we had for example, a cooling tower system like I showed you, it might sound counterintuitive to say, well, what the water that we're bleeding out of the system, why can we, is there any way that we can just recover that back as makeup? Well, that sounds kind of strange, because I thought we were bleeding that because we need to get rid of the system, get it out of the system to replace it with the fresh makeup. But if you treat it to a certain level, yeah, you can certainly do that. And there are treatment systems that exist to be able to achieve something like that. You can get really good paybacks on them. But this is a higher cost compared to the soft water makeup we discussed. So it really depends on the system and what types of challenges and what types of goals you have. But if you're really pursuing water efficiency, this definitely can be something that you consider. So it is an exciting technology. This is what it would look like in a real world environment. That's an example of one that's installed and running. This is at a food and bev facility. And it's a technology that works really well. So just to finish off very quickly, as well, a couple minutes left. Operating cost analysis. This is kind of getting into the engineering side of things, right? So just aside from all the numbers here, it's really just breaking down. There's two scenarios there shown, like our untreated makeup, in this case 3.18 cycles that we're safely able to achieve, compared to a softened makeup. Just close to doubling the cycles of concentration. So again, you've got fixed evaporation, and just all this is doing is calculating how much, what the water usage ends up being on a certain load. So you can see the green numbers towards the bottom right there, or the bottom left, sorry, are showing water savings. There is a cost involved in operating a softener. You have to pay for salt. But there's also chemical savings. So we've got a net savings. In this case, there was an evaporation rebate that we calculated, again, based on the evaporation that we know. So adding up to over $50,000 per year in savings. So you compare that to the cost of implementing, for example, in this case, the water softener, and you see that you probably have a very fast payback on something like this. And then if we compare that to, this is the second scenario on the same system, where we compare the raw makeup untreated with bleed reclaim, which it does have higher performance, over 10 cycles in this case. But the way the cycles work is you get diminishing returns as you go. So once you get past 4, 5, 6 cycles towards 10, then you're still getting benefits, but the returns are diminishing. So as you can see, in this case, the total opportunity was about just over 65,000. So about $10,000 more savings per year. So that is not nothing. But the cost, for example, of a bleed reclaim system is significantly higher than just putting a water softener on the makeup. So you still have that consideration. So it's really, you can get there if you really want to pursue these objectives. But that's where the engineering comes in, is really just helping you understand what the cost is versus the benefits, so that you can make that decision in an informed way. Okay, and then finally, just as far as calling us for assistance with this type of thing. So master specifications are not just for consulting engineers. Some corporations have specs for their own, the way that they have, a quality standard for all the equipment that they implement. We always help with that. It's always recommended to review that type of thing every 3 to 5 years, because things move in every industry. For design assist, if you've got a project that you need engineering assistance with, basically we only ask to be eligible to bid on it, and beyond that, as long as we have time, we'll help you design it. That's no problem. And if it's higher complexity, get companies like WMC involved early, get water treatment involved early, so that if we need certain footprints, or if we need to have certain considerations for supply, and to help you understand the flow rates, things like that, we can find more cost savings and deliver more value if we're involved early in the stage. Okay, on the site survey side, always no charge, no obligation, especially for FBO. Like, we're really trying to deliver value and help in any way we can. So it's a really good way to get a high level opinion, and then we can escalate from there if required, if you want something looked at. Third-party audits, hopefully we never have to do this too often, but it can be done in a way that's not formal as well. But basically, it's a comprehensive evaluation of an existing water treatment program. So if you're interested in that, that's something we can help with. And then we support that with equipment inspections, historic report review, things like that. Obviously, like I said, we're an engineering firm, so we do get involved in forensics and warranty claims and lawsuits and things like that. So kind of the ugly side of things sometimes, but it is something that does have to occur in some cases. So with that being said, hopefully this was an educational, informative for you. We're going to be looking forward to doing more of these types of sessions in the future, other types of systems. So feel free to send us any sort of inquiry as far as if you have questions about this presentation itself, or if you have other topics you'd like us to speak about. But with that being said, if there's any questions from the group, I'd be happy to hear them.
Yeah, John, thanks. This is Nilesh here. And John, thanks for the presentation in first place. It was very informative. It would definitely help all of us. I had a few questions, but we don't have time, so I'll probably send that by email. But maybe just a couple of questions right now. We use normally, instead of an open cooling tower, we are using a closed loop cooling tower, where we have got where we are using the effluent water, effluent treated water which is there. We treat it to an extent where we can use it in the cooling tower. We are just ensuring that that water does not get into the process, and that's why we use a closed loop type cooling tower, where the liquids are different in both the loops. My question is, when we are using these kind of systems, do you have any specific requirements for that effluent treated water, what we are using? Or
Yes.
treating wastewater?
Yeah, a closed circuit fluid cooler. We call those fluid coolers. So basically, you have, if I go back to a diagram, so instead of an open cooling tower where you're using your where you're directly using the condenser water on your load. I don't know if you can see my mouse cursor, but
yes, I can.
Okay. So where you're directly using the condenser water to cool your load, you've got what's called a fluid cooler. So this supply water is going through your evaporative unit
Yeah.
as a closed system. So you've got basically pipes going through this.
Yeah.
So tubes, and then it exits. And then all you have is so you've got a basin of water, and you might be able to even actually run this without water. You can run it as an air-cooled system as well, right? If you drain this,
Canada, yes, we can, when the temperatures are lower.
yeah,
But the countries where the temperatures are normally about 20-25 degrees Celsius average, so
yes,
we end up using water
yeah,
continuously.
yeah. So most of the time you're going to use water when you need cooling. So
Yeah.
it just means, yeah, you can get what's called free cooling if you just if you drain it and you just run it with air, turn
Yeah.
the fans on. But if you have water in here, what you're going to have is you're going to have a spray pump off this that's just going to circulate water up to your sort of your top deck to your nozzles, and then spray that over your tube bundle, as opposed to passing it through fill, allowing it to evaporate. So you will get evaporation from this water, but it's a contained system where your condenser water only exists really on the fluid cooler itself. So the water that goes through here is basically a closed loop. It's inside tubes. So there is treatment. And is this loop on your system water, or is it like a glycol?
No, it's an effluent treated water, not glycol. We are using yeah.
Okay, so it's treated water. So you will anything that runs in a closed loop. The benefit that you have actually with an open system, I mean, obviously the downside is that you're making up water into the system, so it uses water. But the benefit is you're able to reject water, so you can keep it clean in that sense by draining the water. A closed loop has to recirculate the same water over and over. So on the closed loop side, you definitely need filtration, just like any closed loop, whether it's heating, cooling, chilled water, glycol, anything needs filtration, because there's corrosion byproducts that will always come out and will foul the system if you don't filter them out. And then you need some sort of treatment. You usually have either a manual pot feeder, or if it's a large system, you could meter and pump chemical into it. So you'll have some sort of inhibition in there if it's not direct use water. On the fluid cooler itself, you would treat this just like one of these systems, because this is an evaporating system that has it's susceptible to the same things. So as far as corrosion, scaling, microbiome, so you basically have the same treatment package on this. It would just be, usually these systems are a little bit smaller, like less than 400 tons, I would say. But that doesn't matter, that the requirement's the same. So you'd pull off into a loop, you would have your sensors installed, you'd be feeding chemicals back into that loop, and you bleed off of that. The challenge with the fluid coolers is they can be hard to treat, because you don't have a recirculating condenser line that you can just tie into. So sometimes you have to come off the discharge side of the spray pump, for example. The cooling tower manufacturer doesn't always like that, because now you're taking flow from the cooling, right? So you might have to install a line that comes off the basin and returns back to the basin. In that case, you don't have flow, so you need to install a pump, like a booster pump, to be able to feed into the treatment panel. But as far as the treatment, it would look basically the same as this. You need to do all the same things. So I hope that answers your question.
Yep. Okay. Thanks.
Great. No problem. Anything else from the field?
Any other questions?
Not for now. I'll just there are a few which I can just write an email. They were basically on the COC, the cycles of concentration, what we are discussing on. There are a few which I'll just write because we are already 5 minutes past the meeting now, and I need to connect on another call. So I'll definitely send that. I have those emails. I'll definitely send that email, John, to you.
Okay. Sure, no, that's no problem.
Great. Well, there's a question that's been written in. I know we're a little bit over time, but we'll if anybody wants to stick around.
Sure.
What are the most common signs that a current water treatment program is underperforming in a food and beverage facility?
Yeah. So, I mean, a lot of it is just like if you're tracking your costs and your operating costs, and you're seeing there's a few ways that it can happen. So if you're used to certain sort of, the way that your plant operates, and you have costs that your utility costs, and you're seeing a sudden spike of that's not otherwise explainable. Like, you haven't increased production, you haven't added a shift, you haven't done anything other than you're just noticing your costs are going up. That could speak to an efficiency problem somewhere, right? So we should be looking at we should be just having that on our radar at that point. So we don't always, want to point the finger at water treatment for everything. We're in the water treatment space. We always get our finger pointed at for a lot of things. But really, the common signs are really going to come down to just your visuals, your inspections. That's something we stress a lot, and I feel like there's not enough importance assigned to this in the industry to bring the water treatment guys, whether it's third party or your existing vendor, on site when your chillers are open up for inspection, right? And before they're punched, before they're cleaned. That's the report card, right? Of when you open that up, that's how you're doing, right? So taking a visual look in the system, when the cooling tower is shut down for basic maintenance, before it's cleaned, let's stick our head in there and take some photos and see what it looks like. So the obvious signs are just the eyeball test, right? It's really just looking at that system. But if you got a system that's running and you don't have the benefit of being able to, or the luxury of being able to turn it off, really just tracking your operating costs as far as what you think they should be based on the load profile that you have on your system and how you're running, should really point you in the direction of, hey, we should maybe look at the water treatment.
Yeah, thanks, John. The one thing, one of the things our sector is really concerned about is on the productivity side. So, I think everything you're talking about, that avoiding downtime and the efficiencies, I think speaks to a lot of the concerns we have as a sector, because it's a big focus for us.
Yeah.
One other question that leads into that, and again, I think we all try to do this, is how can facilities quantify the cost? When I say we all try to do this, we all try to quantify where the savings are. How can facilities quantify the cost of untreated or poorly treated water over time? Is there a formula or benchmark?
Yeah, so there's no magic formula for everything, but there's a lot of ways you can attack that question. Number one, I kind of showed an example in the slides where, if we go back to that, like these are examples of things that we do, like scenario 1, scenario 2 type things. Just really break down, because we can, at the bottom of this we have, our water rates. In this case, this is a 2021 project that we looked at, but we can pull the from the customer's bills, and not everyone pays the same amount for water, as we know, but we can establish a baseline of, okay, what's our water cost, what's our energy cost, fuel cost. So just for operational things like this, of just from achieving different cycles of concentration, where are we at in terms of the cost difference of running that system, right? So you've got that. Obviously you've got other types of benchmarks. If you're talking about premature failure, you've got corrosion rates that you can measure, right? So if there's corrosion coupon racks installed in your systems, and you're measuring the corrosion rates, you're going to get mils per year corrosion. When you get to a certain number of mils of corrosion, for example, that much metal has been removed from the system, you're going to get into a point where you're having failures. So you can sort of measure the lifespan based on the mils per year of corrosion in terms of rates that you're achieving. So that's another metric that you can use. But really, like as far as costs, it's really just taking an engineering approach of just modeling how you're running now. And obviously there's a bunch of assumptions that you have to make, but you use as much information as you have, and then create the scenario. Here's where you are, here's where you want to be, and then show the difference between those two things. And then over the years, right? And then we compare that to either the investment that might be required, or sometimes there's no cost to making those improvements, or very little cost. So the payback is calculated that way. So yeah, it's not really, I mean, there's lots of formulas that we can go through, and if we're talking about water treatment, but there's no real magic formula for the actual, benchmarking or savings. It's really just looking at each system individually and modeling it and comparing where we're at to where we can be. So if you're in a situation where you're not operating optimally, we'll compare it to the optimal operating conditions, just like, to get a baseline. It was like, here's how far off you are, and just getting it back to normal, what we consider our industry standard. We'll save you this much money before we start even doing anything to improve the system. And then from there, we can go to sort of the next level.
Awesome. Thanks, John. So I know we're over time a bit, but if there's any other questions before we sign off, let us know now.
I have one last question.
Sure.
In operating your system there, how can an operator detect the need for the system cleaning itself, the chemical dose, the loop for the dosage? So when would one know when to clean the system? Is there a typical what's a typical cleaning frequency, and how long does it take?
Okay. Yeah. So if we're talking about the cooling towers, typically a lot of systems are cleaned annually. If you talk to some of the top names in the industry as far as the maintenance of the towers, depending on the criticality of your cooling, you might be doing it more often. And it really also depends on, if you're a 24/7 plant and you just don't have the shutdown time, you just do what you can. But like sort of the manufacturer certified service companies will typically recommend seasonally. So you'd have basically two maintenance events in a year, and you might even have one in between that as like just not a full cleaning and tear down, but sort of just check the belts and lubricate everything and just do the basic maintenance, almost like an inspection, just to make sure everything's running okay. But once a year at a very minimum, and twice a year is the recommended, and that would be a full tower cleaning, properly done, not just power washing the outside of it, like really getting in and cleaning the fill and everything like that, cleaning out the basin, sweeping it out, and vacuuming it, and really leaving it in a clean condition. Because you think about all those little particulates and things like that that are circulating through your system, those erode all the pump seals, and they create a lot of, they contribute to the corrosion and the damage to the system. So the more often and faster you can get those out. Filtration on the system is also really important. We didn't touch on that too much in this talk, but as far as the frequency, definitely once if not twice a year. Twice is recommended. And as far as how long it takes, it's usually about a day's work or half a day's work. Again, depends on the size of the tower, but you're going to have your mechanical service guys on site for about the full day. They'll clean it out, and then usually they have an inspection checklist and a maintenance, as far as preventive maintenance to clean the belts and relube and everything like that. So that's really what we recommend. We align with that as far as keeping the system. That makes the water treatment work a lot easier too, because you have a lot less material in the system that's sucking up the water treatment. You think about biologicals floating around in the system, eating up your biocides. If that's out of there, then you're in much better condition.
Yeah. Do you find that the water the water quality of the water affects the lifespan of your probes on your system, like your ORP probe and your conductivity probe? And what does your preventive maintenance look like on those probes?
Okay, yeah, specific to the probes, great question. The water quality coming in affects everything. So that's really, I mean, it should really be consideration for even like building a plant as far as, you know, what kind of water are we dealing with and what are we going to try to do with it, right? Because that's going to really have a big impact on all of your costs. So specific to probes, for example, if you're talking about maintaining the water treatment equipment, yeah, water with a lot of suspended solids in it, you know, all the way up to systems. There's systems that have permits to take and they take river water directly, or that, you know, they have to discharge into a quarry and draw from that from a canal. There are like specific situations that are much more challenging. But the incoming water quality in general, like if you're, again, just using municipalities like Toronto versus Guelph versus Ottawa, you know, a lot of people are familiar with the Toronto water, Great Lakes quality, very similar to London. You don't have too many issues. The water's pretty clean coming in. The hardness is not too high, so you're not really having any too much of an operational problem with that. But compared to Guelph or Kitchener or something like that, where you have much higher hardness coming in, anywhere where you have a little bit higher heat or just, you know, more nucleation points for precipitate or for scale formation, you could scale up probes and things like that more frequently. Again, you need to operate the system so that you don't have scaling tendencies in it, so you get your saturation index to where it's correct, where you're not forming scale anywhere, and then your probes won't have problems. But even then, you still have, you know, things, other types of contaminants and suspended solids that can accumulate easily on your probes, and they do need to be cleaned. So we like to clean the probes probably twice throughout the season. So obviously on startup, there'll probably be another cleaning or an inspection at least just to check them out during, you know, while it's operating, and then you know, lay them up properly and shut down. That's a big thing with probes is, you know, often they're just left in the treatment system. Just to kind of sit there, and especially if you drain it out, like an ORP probe, for example, does not want to be dry. So there's, you know, you should be laying that up with storage solution. There's a product you can buy called ORP storage solution. So we, you know, I've made even, you know, tees for customers with caps on them that we can actually pull the probe out and install that in there and leave it like that while it's offline. It keeps the probe clean and happy, and then we put it back in, recalibrate it, and it's good to go in the spring. Again, food and bev is often running year round, so that's not really a big consideration. It's more an HVAC thing, but yeah, the probes definitely need to be clean. And the way you'd see that you're having problems with that is when your calibration starts drifting. So it's not reading the same as your handheld meters, or your water treatment company will know this too. Like they have a calibrated meter that they're bringing in and checking against all your probes. And if the readings are drifting by a lot and they're having to calibrate it all the time, or they're not able to calibrate it, that indicates that it's scaled up or failed.
Okay. Thank you.
No problem.
Awesome. Well, with that, we're 16 minutes over, but great presentation, John. Really appreciate the info, and it's very comprehensive for sure. So thank everybody for joining us. We'll be recording this. We'll be posting it on YouTube, and we'll be sharing it. And again, we'll be doing some additional webinars with WMC in the fall. John, anything else you want to add before we sign off?
No, you covered it quite well. I mean, we're obviously directly. I mean, I'm glad to hear that the recording will be posted. And if any FPO members want to reach out to us for anything, as far as, you know, just having a second set of eyes on their system or specifically needing help with a project, that's what we're here for.
Well, thanks, John. Thanks, WMC, and thanks for everybody for joining us today.